Hello everyone. In this lecture, we will discuss two logical operators, conditional and biconditional. Conditional is one of the important logical operators. Let P and Q be two positions. The statement P, look at this arrow, we read it implies or other ways are there, we will discuss later on. So far, so we'll read it P implies Q. So the statement P implies Q is called the conditional statement. Here P is condition. Look at this. Which type of condition is this one? This is sufficient condition. Generally, we discuss two types of conditions. One is necessary, another is sufficient. So sufficient means more than necessary. So here this P is a sufficient condition means more than necessary. And Q is the conclusion. Now in we have another ways to define P implies Q. So we can write this as P then Q. Another way is P implies Q. Another way you can write it P is sufficient for Q. As I told you, P is a sufficient condition for Q. So you can write it P is sufficient for Q. Now another important thing is there. If P is sufficient for Q, then it means Q is necessary for P. So we can write it another way. Q is necessary for P. So this is another way. And finally, another way you can write it Q whenever P. So in this way, this P implies Q, this conditional statement can be written in one of the following ways. You can choose any one to represent this P implies Q or conditional statement. Now look at example. Suppose P is I go to market and Q I play football. So these are two prepositions. Now P implies Q. The first way I can write it, if I go to market, then I play football. You can write it another way. To play football, it is sufficient for me to go market. Look at this, as I told you. P is a sufficient condition. So I can write it in the way to play football. It is sufficient for me to go market. Or you can write it going market is sufficient for me to play football. You write in this way also. Another way you can write playing football is necessary for me. Look at this. As I told you, Q is necessary for P. So you can write it playing football is necessary for me to go market. So in this way, you can represent P implies Q in one of these three ways. Now about the truth table of this P implies Q, because we have two variables P and Q. So in all we will have four combinations of truth values of P and Q. So now we'll check what will be the truth value of P implies Q. Again remember that here P is a sufficient condition, not necessary condition. If this P implies Q means whenever P you are if P then Q means if P is true, a sufficient condition is true, then Q must be true for P implies Q, this statement being true. So now we'll check the different two values of P implies Q. So first case, if this is true, then obviously P, this conditional statement P implies Q is true, because we are saying if P then Q. It means whenever P is true, this Q is true. So both are true. It means this is true. Now look at this is true, this is false. According to this condition, if P then Q must be true, but P is true but Q is false. It means this condition is false. Now the third case, when it is false and it is true. Now look at this, P is false, the sufficient condition is false, but Q is true. It means what about the truth value of P implies Q? P implies Q is if P then Q, but here P is sufficient condition, not necessary condition. It means without this condition P being true, because it may be possible that the sufficient condition is false but the necessary part is there because Q is true. So conclusion is true. It means this P implies Q, this conditional statement is true because without this P being true, because it is sufficient condition. I am again saying this is sufficient condition. Without being this P true, this Q may be true. It means P implies Q. This will be true. Just I can give you one example to understand this in a better way. For example, if I say, if you solve the complete exercise, then you pass the examination. And this, suppose P is false. P is false means suppose you did not solve the complete exercise. This condition is false, but still you pass the examination. It means this condition says that if you solve the complete exercise, then you pass the examination. It means without solving the complete exercise, you can still pass the examination. That's why whenever it is false but it is true, this is true. The last one, this condition is false, this is false. What about the truth value of P implies Q? When this is false, the conclusion is also false. It means it doesn't mean that P implies Q is false. Just remember this. If condition is false and conclusion is also false. But you cannot say this P implies Q is false. It means we are talking about if P is true, then Q must be true. But we are not saying if P is false, what will happen. So it means the condition is itself true. If condition is false, we are not going to check this conclusion. If it is false, then it doesn't mean P implies Q is false. This conditional statement is true because it is saying about when P is true. If P, then Q should be true. It is not saying when P is false. So whenever, if you see these last two one, whenever this condition is false, we are not going to check Q. It may be true or it may be false, but in both of the cases, this is true. It means whenever this condition is false, directly you can say the conditional statement will be true. In the same way, if you see whenever this conclusion is true in these two cases, whenever the conclusion is true, the conditional statement is also true. It means in these two cases, this one and this one, we are not going to check the value of P. This P, maybe look at this here, this is true, but here this is false. It means whenever conclusion is true, as I told you, P is sufficient condition. It may be true, it may be false, but whenever conclusion is true, P implies Q will be true. Similarly, whenever this condition is false, in these, look at these two cases, we are not going to check the truth values of Q. This conditional statement will be true. And remember this concept will be used in the number of cases in other discrete structures, particularly in case of relations function as well. So this is the truth table. The easiest way to remember the truth table of P implies Q is, look at this truth table. This is false in only one case where P is true and Q is false. In all other cases, P implies Q. This conditional statement is true. So there is only one case. In all other cases, this is true. Now, biconditional. Biconditional of two propositions P and Q is denoted by P, double-sided arrow. It is the proposition P if and only if Q, or P is necessary and sufficient for Q. Or you can say if P then Q, if P then Q, and if Q then P, then P. So this is another way to say, to discuss this biconditional. If P then Q, or in short you can write P implies Q. This is if P then Q, and if Q then P. So this is the biconditional. Now look at this example. P is noted by I go to market, and Q I play football. Then P is biconditional. P biconditional Q I go to market if and only if I play football. Or another way you can write it, P biconditional Q, go market, it is necessary and sufficient for me to play football. So you can use any of these two ways to represent this biconditional. Now, what about the truth values of biconditional? Look at this. You can find the truth values of P, this biconditional Q, with the help of P implies Q. First find the truth value of P implies Q, then find the truth value of Q implies P, and finally find the conjunction of these two. So you will get this truth table, and you will see that P biconditional Q is true in the cases when both of the variables P and Q have same truth values. It may be true or it may be false. Look at this. In these two cases, when the two propositions have same truth values, biconditional is true, and other cases when one is true, another is false, biconditional is false. So this is the easiest way to remember the truth values of biconditional. So far we have discussed different logical operators, and we can find the truth values of a given compound proposition or a formula. Now, how can we say whether a formula is well formed? Well formed in the sense that is it possible for we to find the truth table easily? So first we will define well formed formula. A statement that cannot be broken down into smaller statements is called an atomic statement. For example, P, today is Monday, is an atomic statement. And P is the variable of the statement. A statement formula is said to be well-formed formula. In short, you can say WFF, or sometimes we say well-defined formula if it has the following properties. So this from the atomic statements, how can we generate other well-formed formula? So every atomic statement is a well-formed formula. This is the first thing. Now, if P is a well-formed formula, means it is an atomic statement, then negation P is also well-formed formula. Now suppose two P and Q are two well-formed formulae, then P and Q means conjunction and disjunction and conditional of these two. These are well-formed formulae. It means if we have already well-formed formulae, then using this and or conditional, we can form the well-defined formulae. Nothing else is well-formed formula. Other than this, no other formula is well-formed formula. Now, for example, look at this. If you see this formula, this is a well-formed formula. Why it is well-formed formula? Because from this formula, you can easily check that first you have to find the negation of P, because this is inside this bracket. It means if you write P here, Q, it means first you have to write negation P. Then you have to find P and Q, P and Q. Then you have to find the conditional of P and Q implies negation P. P and Q, this implies negation P. So no doubt is there. It means this is one part. So first you have to you can calculate first this one or this one. So means you have to calculate this as a one, this as a one, then finally you will find the condition of these two. It means no confusion is there. So that's why it is a well formed formula. So if you look at this is not a well formed formula, because here no clear instruction is given. It may be possible that if someone is using this interpretation, Q implies negation P. It may be possible that P someone is using P implies Q and negation P. So both of the interpretation may be possible from this one. So confusion is there. That's why it is not a well-formed formula. So now if a formula is not a well-formed formula, then how can we convert into well-formed formula? So for this we have rules of precedence. So the rules of precedence means we have some precedence of logical operators. So first we will calculate negation, then and, then or, conditional and biconditional. So this is the precedence of logical operators, and in which this negation is in the highest precedence, and this order is according to the decreasing order of precedence. So if you take one example, look at this. This is not a well formed formula. So if I have to convert this formula into a well formed formula, then first I will write this parenthesis here, and then here this is negation, then and finally by finally conditional, then finally you will calculate this one. So now it is a well formed formula. So in this way, if a formula is not a well formed formula, then you can use this rule of precedence to convert a non well formed formula into well formed formula. Here some exercises are given for you. Try to answer these questions. This is exercise number 1, exercise number 2, and finally exercise number 3. So in next lecture we will discuss the solutions of these problems. Thank you.